Hi everyone, welcome to the presentation on t-test, one of the basic inferential techniques. A t-test is a statistical test and used to compare the means of two groups to determine if they are similar or there is any significant difference between the two groups. The groups meaning the sample data or two data columns. For example, A/B testing, where we compare the two versions of a web page or email or any other entity, and we have a version and a B version of data. We would like to establish if there is significant difference between the two. Similarly, comparing the means, analyzing data sets, data scientists often need to compare the means of different groups. For example, comparing the average user satisfaction score between two customer segments, let's say segment one and segment two, or the average sales before and after marketing campaign during the t-test. So these are useful techniques that helps data scientists and the business managers to conclude and make a decision. Similarly, for machine learning, also t-test can be useful in terms of feature selection, identifying which column is useful, which column is having a strong influence on the outcome, and also evaluating the model performance. So let's say you have two different models and predictions from two different models can be compared for similarity or uh, too much dissimilarity. So let's get started with the t-test, how it is computed and how do we use t-test in real terms. Some of the prerequisite, a little bit of statistics, essentially probability and data distribution, normal distribution, probability density function, cumulative density function, normal, and also standard normal distribution. The idea about that would be really handy, along with some Python experience. So t-test is a technique where we find out any significant difference between the two data column or two samples or one sample versus a known data point. So let's define t-test is comparing the means between the two groups and to determine if there is any observed differences between the two data series and if the differences are really statistically very significant. So why we need to compare the means of two groups? So variety of reasons, the feature importance and selection, which is very important area of machine learning. And here we would like to find out if there is significant difference in the mean, which can help the machine learning designer to pick and choose the column for the model. The features with the distinct mean means different mean between the groups may contribute significantly to the model performance. So what does this actually mean for machine learning? In a sense that let's say we have two groups of data, let's say the priority one and priority two customers, and the resolution times are measured for priority one and priority two. The mean of this priority one customer or priority one type of complaint should be different than the priority two one. So the features with distinct means, that this is what the meaning is. So the mean of priority one is not similar to mean of priority two. So that is very useful for machine learning. And model evaluation also, let's say you have two different model. So this is your machine learning model one, and this is machine learning model two, and these are the performance scores or predictions, and you would like to compare the two. Essentially, if the two models are equal or similar, the means here also would be similar. If they are not similar, that will also help you pick and choose which model might be very useful. All right, so let's take an example here. Um, Suppose we have a data set and we would like to check if there exists a significant difference in the average scores between the two groups of students. So, for example, the group of students, one group followed a traditional method of studies, and the other one used online method of study. And the group A performed, and there is a score. Similarly, group B also performed, and we have a series of scores for group B. So the hypothesis is the mean of group A is same or similar as the mean of group B, no significant difference. That is the starting point. That's how we set the hypothesis. And then the alternate hypothesis is which we as a researcher or data scientist, we would like to find it out. So if there is any significant difference between the two. So let's say the group A has the scores like this and group B has scores like this. Then we can apply statistical test, which is t-test, and we obtain a t-statistic out of this data set. And then we apply a degrees of freedom, which I'm going to explain in the next few slides. So once you obtain the t-statistic, you can make the conclusion by comparing the t-statistic with the critical value. We will also see how to compute the critical value for a given significance level. And also we'll see another method of p-value, which can also be computed from the t-statistic. Both of these methods are used in concluding in the outcome of inferential technique. So that's my group A and group B data. And the formula or the t-test essentially takes the sample 1 mean and the sample 2 mean and divide by the standard deviation of sample 1 and sample 2. So that's the square root of that. So essentially x1 bar, x2 bar are sample means, and the S1 square is the variance of sample 1, S2 square is the variance of sample 2, and then N1 and N2 are number of samples from each of the group. So this is the formula used by t-statistic to compare the means of two different groups or two different data columns. And this will result in a t-statistic. And if you notice this carefully, the outcome is a number which is called t-statistic, but this is simply going to be in terms of standard deviation. So that's the similarity between a t distribution and a normal distribution that we see in a Gaussian form. So why t-statistic is in terms of standard deviation? Because of the formula that we have, we are rationalizing or normalizing by the standard error or standard deviation. Since we are dividing by standard error, the outcome is whatever number that you get. Let's say the t-statistic is 5. Okay, so this value 5, this means this is a 5 standard deviation in terms of the sigma or a deviation from the mean. So the interpretation of this t-statistic is in terms of standard deviation units from the mean. For example, t-statistic of 2.0 indicates the sample mean is 2 standard deviation away from the hypothesized mean. And that is used in terms of conclusion. And we will see how we make use of this number to conclude if the data columns are similar or if the data columns are not similar. Now, there is one little important aspect that we use in formulating the or creating a t-distribution as degrees of freedom. This simply means the number of samples in your data set. Say, for example, the two data columns, and the first one has 5 values, second one has 5. So we just simply add them and then minus 2. So 1 minus from each of the data column. So that's going to be 8 degrees of freedom. So the intuition behind the degrees of freedom is, let's say a column, let's say this example here, we have a 30-seat classroom, and the first 29 individuals or students can occupy any seat because they are free to choose, but the 30th person has only one seat to choose. There are no options, more than one option given to the last student. So essentially, we have 29 number, which is kind of free Free meaning they have more options to choose. The last one doesn't have the options except the remaining one, the last remaining seat. So we call the number of items or number of values which are free to change as a degrees of freedom. And that's why in our case we have n1 and n2. So we take n1 minus 1 and n2 minus 2, n2 minus 1 as well. And then we add them together. That returns the degrees of freedom. So for example, one sample t-test, we are comparing one sample. So one sample meaning we have just simply one column here. Let's say we have 19 values and we are comparing the mean of this with some mean, let's say 4.3. We are saying the mean here is equal to 4.3 and total number of samples 19 here. So degrees of freedom, in this case, we will consider 19 minus 1 is 18. All right, so this is the intuition behind the degrees of freedom. Now, this degrees of freedom also influences the t-distribution. So the use of degrees of freedom in statistical inference is to get the critical value of a given distribution for the alpha or significance level that we have set. So let's see the example how degrees of freedom affects the outcome. So if you look at it, here I've taken degrees of freedom 1 and 2 and 3 and 30. Okay, so let me then show you how degrees of freedom actually changes the shape of the curve. So this is degree of the freedom 1, and that's the blue one that you see here. And this is your degrees of freedom 1. So when you have degrees of freedom 1, the t-distribution looks like this. Okay, and then as you increase the number of samples, the degrees of freedom um, increases, and hence the shape of it. For example, last one is this one here. Okay, so this is the degrees of freedom 30. So as you increase the number of samples, the degrees of freedom also increases, and the t-distribution is now approximating a standard normal distribution. So t-distribution is similar to normal distribution in shape, but the degrees of freedom is important in determining the shape and the outline of the t-distribution. So essentially, the t-distribution versus the normal distribution, the similarity that we saw, it is similar to normal distribution, but the t-distribution has slightly heavier tails compared to the standard normal distribution. But if the degrees of freedom is increased with the number of samples that you have in the data columns, then t-distribution will be very similar to Gaussian standard normal distribution, which is a mean of 0, standard deviation of 1. So t-distribution actually helps you, uh, spread out the extreme values. So that means you have more room to play with it, and you can then reject the null hypothesis because you have a wider range of values available. So that's the impact of degrees of freedom. Lower degrees of freedom, small sample sizes, and that means the t-distribution is heavy and thicker compared to a normal distribution. And this also means greater variability in the shape of the distribution. And that means that hypothesis testing for larger values, it is pretty hard to reject a null hypothesis because you have to get a large statistic to compare against the critical value. And the critical value also increases with the degrees of freedom, and hence it is pretty hard to reject. And that's why t-test or t-distribution is very useful in making a decision. And just the opposite with the large sample. Sorry, I talked about the large sample size, and with the lower sample sizes, then the t-distribution is kind of having that characteristics of wider room for making decision. With a high, it is actually similar to standard deviation or standard or normal standard normal distribution, and it becomes less heavy and distribution becomes more peak. If you see here in this, as we go with more number of degrees of freedom, this is more peaked compared to the blue one, which is less peaked here. So that's the difference and the impact of degrees of freedom on t-distribution. So the summary on degrees of freedom: smaller degrees of freedom, more variability, heavier tails, and is good for t-test. Larger degrees of freedom, less variability, and it is very peaked distribution. So you don't have that range of values to really make good use of in the inferential technique. So let's now compute for group A. So first step is to compute the mean of for group A, and similarly standard deviation for group A, and number of samples is 5, and repeat the same thing for group B as well. Put those values in the formula for t-statistic, like sample mean and sample mean of the other column, and the standard error for each of these. And this is the t-statistic that we were talking about. So this is now going to be compared against the critical value. So we need to now understand for t-distribution, how do we get critical value or a threshold value corresponding to the significance level that we choose. Let's say we choose a significance level of 5%, then what is the corresponding critical value? We need to then compare this t-statistic with the critical value. And if this t-statistic is more than the critical value, then you can reject the null hypothesis. All right, so the t-distribution has a formula, something like this. And here the key thing is we are going to use the degrees of freedom. Let's say for sample set, here you 11 number of rows, here 15 number of rows. So the degrees of freedom will be here 15 minus 1 plus 11 minus 1, that's 14 plus 10, 24. Okay, so we plug in 24 here, and then the t-statistic we just computed. So this is going to return you a probability density, which is called t-distribution. Essentially, this is a probability density function that we normally see in Gaussian distribution. So the t-distribution is also similar to Gaussian. You need to additional piece of information is the degrees of freedom, and it's going to return you a t-statistic, or simply a value which can be then used to compare against the critical value. So I'm going to simulate a bunch of t-statistic, let's say from 4 standard deviation on the left hand side to 4 standard deviation on the right hand side, and we will simulate 1,000 points in between. And for each of the t-statistic, we will generate a PDF. All right, so this is the formula that I'm going to use to generate the PDF. So next step, so this is my PDF for the values of the t-statistic between -4 to +4 standard deviation, and these are my probability density values. And this is pretty much similar to standard normal distribution if you look at it carefully. Only difference would be at the tail with a lower degrees of freedom. Now with the PDF, you can compute the cumulative density function also. Exactly this. So let's say you have a point on the PDF, let's say here. So the cumulative density function would be all of the PDF values accumulating or accumulated at this point, and that point would be maybe somewhere here. And likewise for another point on this side, this will be the cumulative and this will be the cumulative, and finally this point probably would be this point here. All right, so this is my cumulative density function, this is my probability density function, and we're going to use this to compute the p-value for inferential statistics or inferential tests. All right, so now we understood the PDF and CDF of a t-distribution, which is very similar to a Gaussian pattern. So the t-statistic that we found was -0.247, and that appears somewhere here. And as you notice here, it's appearing on the left-hand side. So this is the mean here. All right, so this is the mean here. Now minus 0.47. So this is on the left hand side here, right? So this is my CDF, actually, the cumulative density function. And let's say that cumulative density function value is zero point 0.4. That means it is 40% probability of observing a t-statistic of 0.247. That is the meaning of the cumulative value here, or cumulative density function. All right, I hope it is clear. So we're going to use this idea of CDF, or cumulative distribution function, to come up with p-value. So how do we compute the p-value now? The p-value now is computed basically, if you look at it, let's say my significance level is up to this point. So we are interested in the region on the right hand side. So this is going to be 1 minus of whatever CDF on the left hand side. So it's going to be 1 minus of this. All right. And that is your p-value. So if the statistical test returns a p-value which is in this region towards the right hand side, then we can reject the null hypothesis. That's the intuition behind the p-value computed from a t-statistic. Now, in this case of t-test, p-value is simply 1 minus of the t-statistic that we have computed, and then we multiply by 2 because this has a two-tail test. That means we have something like this. Now, it could be possible that the value, let's say we are talking about the mean is 65, and your t-statistic is saying, oh, okay, mean is not equal to 65. That not equal to means either it could be greater than 65, it could be here, or it could be lesser, very, very less than 65. So there are two possibilities. And because of that, we multiply the probability density function that we just computed with 2. So this is your PDF now. So this is 0.81. Okay, this is a highly probable. So if you get a very low value, let's say 0.0001, that would fall in the extreme region. Okay, so if your computed p-value is lesser than 0.05, which is your significance level, we can reject the null hypothesis. So this is a relation between the p-value and t-statistic. Okay, so let's take an example here to really understand the relation. Let's say we have a t-statistic of some value, statistic, and that value is whatever n. Now for this value, we have a PDF, so we can compute the PDF. And then from that PDF, we'll obtain the CDF. Okay, so let's say this is having some PDF. That means this is my t-statistic, and that's my mean. And here, my t-statistic falls somewhere on this point. Okay, and the CDF that for that t-statistic is, let's say, 97%. So the p-value here will be 2 times the minimum of t-statistic CDF, which is 0.97, and then 1 minus of this, so this is 0.03 or something like that. So this is going to be 2 times minimum of these two. So this is minimum of, so this is going to be 0.06. That's my p-value. Now this has to be compared with the significance level that we have set is 5%. So that 5% is about 0.05. Now this one, 0.06, is actually more than 0.05. So that will not fall under the rejection region. For example, here, this is my 5% area, for example. Now I am into the 6% area, which is not into the 5%. So I cannot reject the null hypothesis. That means we have to accept whatever is the null hypothesis. If the mean is 65, then we need to accept that. So we are failing to reject the null hypothesis in this case. So this is how you compute the p-value from a t-statistic and compare against the significance level or a critical value. In the next step, I will also show you how to get the critical value for a given significance level. Okay, so let's now talk about why do we do twice of the CDF? Because of the reason we have two tail. Either the value can be greater than the hypothesis or could be lesser than the hypothesis. If it is not two tail, then we are not going to multiply by two. We'll just take the 1 minus of the CDF. So you have to consider whether it is a two tail test or the one tail test to compute the p-value accordingly. So this is why we multiply by 2, basically account for the left tail and also account for the right tail in a two-tail test. If the test is only one tail, means either greater than or less than, then we are not going to multiply by 2. All right, so significance level determines how much of room I have to make the error or accept the error. That's called significance level. So if you're very confident that your data or your mean is true in almost all the cases, so you set the null hypothesis like 95% or even more than 99% as well. So for example, medical medicines and some of the critical domains, we go with a very high significance level. For normal data, enterprise data, images, and numeric data, which is not very critical, we use 5% as the significance level. So for that 5%, we have to compute the critical value, which is nothing but a statistic, and then we compare the statistic with the computed statistic to make a decision. So commonly used significance level is, let's say, 5%, 1%, or 10%. Now, depending on the problem statement and how much of error you can really absorb, you set the margin or significance level. So critical value is a threshold or cutoff used in the hypothesis testing to actually reject the hypothesis or accept the hypothesis. So beyond the critical value, you're going to reject, and within the critical value or lesser than that critical value, you're going to accept or rather fail to reject. So deciding a critical value, if the absolute value of your test statistic is greater than the critical value, then you reject. Otherwise, you accept it. So the decision is there are two ways to decide. One is the p-value less than 0.05, or you have a t-statistic which is more than the critical value. Then you reject the null hypothesis. I'm going to show you a little Python code to talk about the distribution and perform the hypothesis test. So this is the Python code where I'll be showing you how to plot a t-distribution. And this is simplified, dummy data that I'm using here. So this is a function which defines the t-distribution. Two parameters that are needed. One is the t-statistic and the other one is the degrees of freedom. And degrees of freedom is nothing but the number of samples in your data set. So this is little function that I have which computes the t density function. So I'm going to use a gamma, which is a standard of of Python function called math library, and then we call the gamma, and then we provide the degrees of freedom and also the t values here. So we will be taking a range of t values, and then for each of the t value, we'll have a PDF. So the idea here is to take a range of value, let's say -5 to +5, and we take each of these t value, which is essentially t statistic, and then for each of this, we will plot or we get the PDF. So essentially, the PDF is coming from the function that we just wrote here. So this will be a PDF, this will be a PDF, this will be a PDF, and then likely it will take a shape of a normal Gaussian pattern. Okay, so this is what I'm going to demonstrate now. All right, so that's my function, which is going to take the input as range of t values, t statistic, and the degrees of freedom. All right, so let's say this range is -4. So it's up to you. You can take a range of minus, not necessary that it has to be 4. You can go up to 7, and let's say another 7 on the right hand side. And let's say we have 1000 points in between. I need to run the first few lines as well. All right, so now the degrees of freedom I'm choosing at 8 because that's the number of samples I have, for example, and then I can do a simple plot. So here is my plot, which is taking the t values, all the possible t values, and then for each of the value, we are getting the PDF value. We got the PDF values in the earlier cell, and then we're going to plot them. So this is the plot that we get here, and this is your degrees of freedom 8. And I'm going to change the degrees of freedom. Let's say I'm making it degrees of freedom 2, and now let's see if the shape is changing. Yeah, shape has changed. It's become more wide. So less degrees of freedom, it allows for greater variability. As you increase the number of samples, then it approximates to standard normal distribution. So from this, you can also compute the cumulative and probability density functions. I'm going to use the SciPy package to demonstrate that, not manual method. So this package does almost everything here. So I'm going to use the T module of SciPy to do exactly what I did in the previous step. So here, for all range of t values and the given degrees of freedom, I'm going to obtain the PDF value, which is similar to what we have done before. And then I do not want to do manual, finding out the CDF. I'll just use this package to get me the corresponding CDF of a particular t statistic. So that's my cumulative. Now we're going to plot the PDF and also the cumulative density function. This is how it looks like here. All right, so where is the t statistic that we had in our slides? 0.247 minus. And that you can show also in, so essentially you need to find the CDF of that particular point and then mark that particular CDF on your overall cumulative density or distribution function. So this is the point which corresponds to the t statistic of minus 247. All right, so now this is how we make use of PDF and CDF. And as we discuss how to find the p-value of a two-tailed test, you take the t-statistic and then also take the 1 minus of the t-statistic CDF and then multiply by 2. So you get the p-value. This p-value has to be compared against the significance level or the room for error. So this one is pretty high, nowhere near here, so you will not be able to reject the null hypothesis. So you have to accept it. Okay. Now, so this is how we make use of, and this plot is for varying, degrees of freedom. Let's say 1, 2, 3, 4. This is exactly the plot I showed in my slides earlier also. So then next, I will be showing a bit more detail about the PDF and CDF. Okay, so let's look at another example as to how this PDF and CDF are used in hypothesis testing or T test. So I'm going to use the similar data here. Let's say I'm generating data which is having a distribution, something like a normal distribution, some dummy data here. So let's perform a t-test. So I'm using the data and say that whether the data has a mean of 120 or not. And that data is sitting in the samples. So if you really look at the samples, it contains all the data sets. So let's look at that. So this is the data, and now I'm saying whether the mean of this data is around 120 or not. So this is called one sample t-test. So the outcome can be that it is either less than 120 or more than 120, but not 120. That's the counter hypothesis that we will use. Now, how to perform this test is basically one-liner. Put the data samples as a parameter and the test value as a reference mean. These two things you have to enter here. It's going to return the t statistic and a p-value for you. Now, number of samples, and -1 is my degrees of freedom, and my t-statistic computed by the SciPy package is 5.86 and a p-value of very, very low, something multiplied by 10 to the power -7. That is way, way, way less than 0.05. So you can reject the null hypothesis. So in this case, what is my null hypothesis? My null hypothesis is the mean is indeed 120. Okay, so that's my null hypothesis. The alternate hypothesis is mean is not 120. Now my p-value that we got is way, way, way less than 0.05. So we can now reject the null hypothesis. So our data shows the mean is indeed not 120. It could be either greater than or less than 120, but not 120. So this is the decision making that we have done using the output here. Now, to illustrate this using a plot is really interesting. So I'm going to take the range of t values, t for tiger, and -7 to +7, and then we generate the PDF for each of the t values. And then after that, I'm going to show both x and y on a plot, and then I'll show you the t statistic as a line. So t-statistic is what you computed here. And then after that, I'm showing you another line here, which is with the red color. That's my critical value. So let's see the outcome here. So this is where your t-statistic is falling 5.87. All right, and that's my t distribution here for degrees of freedom is 49. All right, so now I need to compare this red line with a critical value. Now I need the critical value as well. So the p-value I computed just now can also be manually computed, and this is the same as what you got from the package here. Using the package also, we got the same value as here, like the manual method. So next step is I'm going to show you how to get the critical values for the significance level of 5%. So let's see how it really appears. So I'm going to compare now with the critical value and the just one second, I need to run this line as well. Yeah, so this is my t statistic of 5.87, and you can actually now compare with the critical value. What is the critical value for the significance level of 95%? So that critical value would be some value, not 5, because that's really high here. And you can now compare here. In the next plot, this is my critical value. The blue one is my 95%, which is basically 2. Value of 2 standard deviation, but you got a value of 5.87 standard deviation, which is really really ahead or towards the extreme region. So what it means is after the blue line is my rejection area. So if your t statistic is falling in this region, which is the case here because it's in the rejection area, you can reject the null hypothesis. So this is the intuition we apply in all of the inferential techniques here. Yeah, so let's come back now. We saw the example of a t-distribution from intuition perspective, and we saw how we use a t-distribution to get the PDF and CDF and compare against the critical value. The next few topics on t-test will be what are the types of t-tests that we normally use. So one is the one-tailed means directional t-test. Here we are looking for difference in one direction. For example, group A has a mean which is greater than the mean of group B. So that's an example of directional t-test or rather one-tailed test. Two-tailed test would be where there is no direction. It could either be left or right, greater than or less than. So the tails simply means that direction. So if the average score of group A is significantly greater, does the new drug lead to a decrease in the blood pressure? So you notice here the direction, decrease and significantly greater. Is there a significant difference between the mean time between the two interfaces? Slower, right? So that's also direction. Two tail has no direction, so you're just saying significant difference. That's it. So are there differences in the average customer satisfaction scores, right? So there's no direction here. So types of t-tests that we normally use based on number of samples. So you could have one sample t-test or two sample t-tests, or you could also use the based on the type of samples. For example, you have independent t-test. That means the groups of data. Let's see, group of data one, group of data two, and the values here and the values here have nothing to do with each other. For example, customer rating. So this can be just a rating, and here also can be rating. So nothing to do with each other. So that's the independent um, t-test. Other example could be group one, let's say patient one, patient two, patient three, and that's the before the medication reading, after the medication reading, before the medication reading, after the medication, before the medication. So when you have this kind of a related data, that is called paired sample t-test. All right, so we're going to see the Python demos for all the variants of t-tests, how we perform those in Python. Okay, now we see how we make use of the probability density function and cumulative density function, significance level, critical value, all of that in the implementations of a variety of or other variants of t-tests. So some of the variants that I've mentioned here or I've developed the code for. So one sample t-test, two sample t-test, one sample left-tailed, and one sample or two sample left-tailed as variations. And this should pretty much give you an idea of the type of t-test that we can implement. So the package that we use mostly are SciPy statistics package, and here is the package for one sample t-test. And similarly, we have a separate package for two sample as well. So let's see how we do one sample t-test. So this is the formula we use for one sample t-test. So here is the sample mean, and this is the reference value. For example, I have a series of data regarding blood pressure measurements, and we would like to check if these measurements are similar to a known value of 120. So this is called one sample t-test. So now the null hypothesis here would be that yes, the mean of the sample is indeed 120 because that's the common belief. The alternate hypothesis would be the mean is not same as 120. So let's proceed here with this data set. And this is my population mean. Perform the one sample t-test, provide the data and the population mean is going to return you the t-statistic and a p-value as we discussed in the previous demonstration. So this is my t-statistic and a p-value. P-value lower than 0.05 is significant in terms of saying that the mean is not, or you can reject the null hypothesis. Here is way less than, far less than the significance level of 0.05, so you can reject the null hypothesis. All right, so let's say here my 0.05. Now, if this were something like 0.01, then you have to compare against 0.01. Now, critical value can also be computed for the given, alpha. Let's say the alpha is 0.05. So I can, since this is a two tail, so we can, or rather, 1 minus the alpha by 2, and that should give you the percentile. And when you get the percentile, that is basically the t statistic that you get. and that is actually the critical value. So here my critical value is 2.09 for a two-tail test. So now we can compare here using the plot. So this is my t distribution. The red ones are my critical value on a two tail test. One sample t test means two tails. So I would like to use one sample, but the inference can be either direction. So, and my computed t statistic is on the right hand side, and that is outside of the even the rejection region here. So that means you can reject the null hypothesis given this case. So another variation of a t-test is called two sample t-test. And here I'm going to use two sample x1 and x2. This is the formula being used by the package inside. So the data series here, female blood pressure and the male blood pressure. And we would like to test if the mean of female and the mean of male are similar or not. So the null hypothesis would be that the means are similar. The means of female is similar to means of the male. And the alternate is they are not equal. So not, when we say not equal means either way, right? Either could be lesser or greater. So this is two sample, two tail test. So, and now I'm going to use a package which is independent. Okay, so it's different than the one sample t-test. So again, pass the data series, both of these data series, and it's going to return the t statistic and a p-value. And the p-value is very, very less, so lesser than the alpha, which is 0.05. So you can reject the null hypothesis. Now you can also do a plot to visually see this. And as in the previous case, we are going to determine the critical value, lower and upper, both, because this is a two-tail test. And, uh, and let's plot both of these along with the test statistic. So the red one, the red lines are your critical value on the higher side. This is on the lower side. And this is my rejection area. The shaded area is rejection. And this shaded area is also rejection area. Now, where I'm getting my computed t-statistic, which is the green line here, and that's way outside. That's into my rejection area. So I can reject the null hypothesis. So some one more variation here, one sample, left tail test. So now I'm saying left. Left means lower. So I'm going to use my data series. And hypothesis is, let's say, 110, for example. So the null hypothesis would be that the mean of this data series is actually greater than or equal to. And then the hypothesis that you have, the alternate hypothesis would be what you want to test it out. You are saying less than, right? So less than means the mean of the data series is less than 110. That's your counter hypothesis. Now I'm going to perform the one sample t-test. Make sure the data is presented in this order. So we are talking about the female blood pressure readings and the hypothesized mean, and the alternative is less, means it is the one tail on the left hand side. So that's why you provide less here. I'm going to return the t statistic and a p-value. So here the p-value is significantly high, is greater than the alpha. Let's say the alpha is 0.01. So we cannot reject the null hypothesis, and that means you have to accept it. That means here, whatever is your null hypothesis, that it is greater than 110, that holds true. So let's get the critical values here. Now notice here the critical value is left tailed, right? So that's on the left hand side. So if you plot, so here look at this right hand side, there is no rejection area. This is the rejection area, the shaded part. And my computed t statistic is on the right hand side. So you will not be able to reject it. So your null hypothesis hold true. And same way, you can perform one sample right test, right tail. For example, this is my data series, and my hypothesis is 110, and alpha is 0.01. My hypothesis just the opposite now, and what you are trying to prove will be your alternate hypothesis greater than 110. Perform the test, and then you get the null hypothesis, very sorry, p-value, which is really small, so you can reject. So let's now, you can also plot. Let me see, I have the plot here below. So compute again the critical value and plot it. So I'm saying the right tail, so we're talking about right, and this is where your t statistic is way into the rejection area, so you can actually reject the null hypothesis. So two sample, left tail again, another variation of t-test. So let's say two samples, there are two samples, and now you're saying one sample is smaller, or the mean of one sample, let's say female, is smaller than the male. Okay, so that's my data set. Alpha is 0.05, and then we perform the t-test here. And here is my data series 1, data series 2, and the alternative is less because we're trying to say the female mean is lesser than the male mean. So it's very important to set up the data correctly, otherwise you get the wrong results. So the output is pretty high p-value, you will not be able to reject it. And likewise, you can also do the plot of the t-statistic and a critical value. So this is a two sample left tail. So the rejection area will be on the left hand side. And this is the t-statistic, which is not in the rejection side. So you will not be able to reject it. Okay, so these are the various combinations of your t-test typically used in the decision making. Um, I hope this demo was useful. And then we go over to the content slides now. Okay, so now we are back to the content slides. Here we previously talked about the examples of t-test, one sample t-test, two sample t-test, and also the direction less than and greater than, those examples. But there are some assumptions to check before you apply or perform the t-test. The assumptions about the normality and homogeneity are important considerations. Normality means the data that you have or the samples must follow a normal tendency or normal distribution tendencies. And this assumption is especially useful for larger sample size. Let's say the sample size is 100 or 150, then make sure the data is normally distributed. Let's say the female blood pressure, the male blood pressure readings, they should follow a normal distribution or a bell curve. The other one is the homogeneity of the variance. That means the data set or the sample sets, the variances of the two groups must be similar. So this is not applicable to one sample t-test, but this is applicable to two sample t-tests, where the variances of both the groups must be more or less the same or similar, not exactly same. It's never going to be exactly same, but yeah, so that these are two important considerations. And apart from that, we have a random sampling. The data should be randomly sampled and independently sampled. So these are three essential important considerations in t-test. So checking the normality of the data, how can we check the normality of the data? There are few techniques. First one is using a visual technique, which is a QQ plot, quantile plot, where you can compare your data samples against the hypothetical, normally distributed data. If they align to each other, that means data is normally distributed. For example, here the red line is your hypothetical normal distribution, and the blue dots are your actual data. And you can see pretty much normal. So in this case, but if the blue points are deviating quite a bit from the red line, that means the data is not normally distributed. So you cannot use t-test in that condition. And then similarly, you have statistical tests as well. So now you have other statistical tests to use, or you can make use of those tests to check for normality. I'm going to show you the Python code for both of these. So that's the checking the normality of the data. Now, checking the homogeneity of variances, and this can be checked by using another hypothesis testing, which is Levin's test. This is also I'm going to show you in the Python code how you can use Levin's test to check for the similarity of the variances in the groups or samples. Is applicable to two sample t-test, not for one sample t-test. All right, so why we need to check for assumptions? Because this is how most of these statistical tests are uh, based on. So it makes an assumption that the validity of the data must be ensured in terms of normality and the spread of data. This is why we're going to check for assumptions. But what if the data does not meet those assumptions? Then we have to look for alternative to t-test. And in the next video, we'll talk about those alternative called non-parametric statistical tests. For t-test, there are alternatives to uh, situations where data is not meeting the normality and the homogeneity of data variances. So we can consider a few tests called, one of them is Mann-Whitney-U test. And this is, I will be covering in the next video. Thanks for watching. We'll see you in the next video.